Hello, this is Gus from 3DeepLearner.com, and this is the first video in our SIGGRAPH 2018 series. So in this series, I'm going to be covering the four papers you have voted as the most interesting in this year's event. And these are all papers that rely on deep learning, which is the topic for our blog. And I'm going to do short videos that are digestible versions of this paper, okay? So this week I'm going to talk about fast and deep deformation approximations. This paper was authored by some guys that work at Berkeley and DreamWorks. And what they're trying to achieve is to approximate the complexity of deformations that one has in hero characters for feature film animation, but with low computation costs. So in a feature film, your hero character, it has very complex deformations. Sure, you start with your basic skin binding, but then you can add a lot of corrective blend shapes on top of that. You might add some procedural deformers to bulge, the geometry twisted, do some squash and stretch or something like that. You could also simulate some skin jiggling. You could do muscle simulation. So you can compose the deformation from different operators, different parts, and these things really add up in computation. So their goal is trying to achieve maybe not the exact same result, but something, that is okay to the human eye and in real time. So the way they did this was using neural networks. So neural networks are known for being very good universal function approximators. So you can imagine if you have a function and you have an arbitrary input and you want to extract an arbitrary output for it, so long as you have examples of what those inputs and outputs look like, your neural network can pretty much approximate that. Of course, different problems have different characteristics, but this is a really good tool to solve this problem. So in this particular problem, what they're trying to solve is this. They have an input movement and they expect an output deformation. So the examples you would need would be the skeleton moving and the mesh, and the neural network will establish a correlation between these two things. Neural networks are also known for being very low cost in computation. So you might have heard that recent developments in machine learning are due to the huge amounts of computation we have, and that's true. But neural networks, they work in two phases. You have the training phase, which is actually, it's intensive in computation. And then you have the prediction phase, where you actually use the neural network that has been trained. And that's really fast. That's just some matrix multiplications that your CPU or GPU can do in no time. So that's what you would use in real time. And it's fast. So in theory, neural networks would be a good way to solve this problem. But how did the authors go about doing this? So let's talk about the implementation. So they created a neural network, which is a very simple kind of neural network, or at least the simplest neural network topology, which is a fully connected neural network. So you have 4 layers, and these layers are all fully connected, like this. So for every neuron in one layer, there are weights connecting it to all the other neurons. Okay, like this, and so on. I think you can extrapolate from this, right? So every neuron in one layer affects the neuron, every neuron in the next layer. And as they have created one neural network per character joint, the inputs for the networks are the transforms for this joint, and the outputs are the displacement for the mesh. So the actual deformation that joint has caused. So you have 12 neurons in the first input. With these 12 neurons, they are like the 3x3 matrix that describes the rotation and scaling, plus the 3 vertices that describe the position in local space. This is all local space, okay? 3 is position. So 12 neurons. And then here in the output, you would have as many neurons as you have vertices times 3, because, you know, the first neuron would be the x displacement for the first vector vertex, and then the y would be the y displacement for the first one, then the z would be the z displacement, and then the next one would be the same thing but for the second vector, and so on. So you would have as much neurons as you have vectors times 3. Okay, and then you can you need to give it as many examples as you can for joint transformations and corresponding displacements, and then you would train this network, and in theory it would learn the correlation between both of these. And they tested it and found out that it actually does. Just talking a bit about this topology, they use 2 hidden layers. They both have this 512 neurons, and this is, I mean, it would work if you use more or less, and the authors don't explore much why this was the number, but it's common in neural network papers that, you know, this might be tested or not. So if you have been following our blog, we have already posted one article on how neural networks work. If you read that, I think you pretty much get this. It's not that hard. Why this would work? If you haven't done that already, I would encourage you to do that. The links are in the show notes, so please check this article first. And if you have done our tutorial on how to train a neural network, that's pretty much the same thing that you have done before, just with different data, okay? The only difference between this network and the tutorials we have put out already is that this is a regression network. And the ones I have showed you before are classification networks, okay? So this only means that in a classification network, you're trying to classify something in categories. So let's say the bone would be moving, and I would say, oh, this is a jump movement or a walk movement. And here we don't care so much as to classify this into categories. We only want to get this output values, and we hope that they match the examples that we give the network. So there's a slight difference in the network, not in the topology, but in the mapping functions and in the loss functions. I'll talk about this a bit. So in a neural network, every layer gets, after the matrix multiplication is done, the values are remapped. So in a classification neural network, here, and here we have the regression. Okay, so in the classification neural network, you would have, let me try to get some other color here. You would, what you want to do is you want to find out which of these neurons has the highest value, the highest activation. And you want to get that so you know which category is the winner. So this is your winner. So the function we use to remap the values and find this information is the softmax. So it's basically a max, but you don't throw out the other values, you just diminish them. So it's called the softmax. And that's what you use when you want to do classification. But when you want to do regression, you don't want to do that. You don't care about the winner. you just want to remap whatever activation values you have in all of this. So you care about all the neurons, not just about the winner. And you want to remap that to the actual examples in your data. So what we do is we use a linear mapping. Okay, so let's say your activation goes from 0 to 1, and your displacement in the x-axis for the first vector goes from -2 to +3. So you want to remap this to that. And that's what the linear function does. Okay, so that's the first change in our neural network. And the second one is in the loss function. So there's something in a neural network training that is called the loss function, which actually determines what is the neural network trying to optimize for. So in a classification neural network, you're trying to optimize for having the most correct results as possible. So in each epoch of the training, you want to predict the winner that is matches your sample data. And the loss function that calculates if you're doing that correctly and in which direction the neural network has to go to continue learning is called the cross entropy. Okay, so it checks if it has gotten the winner right, and if not, it tells the neural network which direction it has to go to continue learning. But in a regression, that's not what you want to do. What you want to do is you want to minimize the distance between your current prediction and the actual values that you want to predict. So it's not so much a matter of accuracy, but of distance to the correct result. So you're trying to minimize distance, and for that you use the mean squared error loss function. Okay, so this is called MSE for short. So that's all you need to do. You just change 2 keywords in your code. You don't have to implement anything new. Just change this and you go from a classification to a regression network or back. Okay. So this in Keras, which is the framework that we have been using so far, all you have to do is you change your activation and you change your loss function. Okay, so that's all you need to do. We changed the metrics also, but that's just for visualizing. This is what actually changes the training. So now let's talk about the inputs and outputs. So inputs are just the transformations of the joint. Okay, in the paper, as I told you, they use the 3x3 matrix that defines the transformation. So that would be like 1, 0, 0, 0, 1, 0, so forth, plus the 3D vector that defines the position. Okay, and the outputs, I told you those are the displacements, but you know, displacement could be many different things. It could be the displacement from the bind poles, or the displacement for the linears from the skin bind. What the authors actually went for was a displacement from a skinning that it doesn't have any blending between bones. So it's just like creating clusters in Maya and skinning your character that way. So you can see here there is no blending. It's a matter of either this joint or this joint. And what the network is learning is the displacement from this vertices to these vertices. So something like this. Okay, so these red arrows are what the network is actually learning. All right. And it works. It works great. I guess this is probably something about performance. So I guess that's what they chose it. But it would work if you chose other kinds of displacements also. So something else they did with the outputs, they tried to minimize the number of outputs they have. So you can imagine you could have a model with like 50,000 vertices, and then you would need 150,000 outputs in your neural network, and that might not be practical. So what they did is they masked out zero influence vertices. So for example, let's say this joint only deforms these guys right here. Then you would mask out the whole model, everything but this. That's really common sense, but you should do. And then they use a technique for dimensionality reduction called PCA. If you don't know what PCA is, I really recommend you looking into this. I'm not going to go into this video, but it's a really nice statistical technique for dimensionality reduction. And dimensionality reduction is nothing but kind of like a lossy compression. So you have a method for reducing the amount of data you need, but you lose some precision, but it could be a good trade-off. Okay. So this is how they actually implemented it, and I have an example of the prototype implementation that I did in Maya. Okay, so this is not the actual code that was created by the authors, but I followed their instructions and it's pretty similar and it works. Okay, so right here I have a model that has some custom deformations. So I have this lattice right here, this FFD, and this FFD is triggered by the rotation of this joint right here. So you can see there is like a set driven key, and I have also some sculpting I did to show the elbow, and I pinched the skin a little bit whenever this joint bends, and then whenever this joint twists, there is some stretching, some twisting in the skin, and so forth. Okay, so this would be my hero character example, and right here I have the linear skin, so no blending, just either joint 1 or either joint 2, and then I got the displacement from both of this and trained a neural network just as has been described by the authors. Okay, so then I plug my deformer. I've created a deformer in Maya using Python. It's called TDL, 3DeepLearner, FDDA, and it should work. Okay, so now I have the deformer, and I gotta plug the joint transformation here. Oh, just do this. Okay, so now if I play this, let me move my, okay. So as you can see, this is now the model that is being approximated by the neural network, and it looks pretty much the same. I mean, I'm sure if you subtract one from another, you can spot the differences, but if just visually, it's really good. Okay. See, it's pretty much the same deformation. Okay, I'm gonna share this in a post. This should be online already, and you can download and see all the instructions how I did this. You can download the Maya scene, the Python notebook to train it, and so on and so forth. Okay, so discussion. So what is interesting about this paper? There are many things that are interesting. The main focus of the authors is speed. They show examples where they get like 10 times the speed or that they would have if they had to calculate all the deformers and so on. So that's really nice. Another interesting aspect is portability. So as you can see right here in the example I have showed you in Maya, I had this deformation and I have this other deformation that is created by this pose interpolator. I mean, imagine trying to move these. This is just very simple. There's a lot of things that are much more complex than this. Imagine trying to move this to a game engine, or you might want to move your hero character to Houdini to do some crowd simulation and so on. You're gonna have a hard time reproducing a complex rig. And doing this, all you need is a very simple skin binding, and the neural network will take care of doing the rest. So I think this is even more interesting. I mean, it's great that you can do it with speed, but it might be even more interesting than just the speed aspect. So portability is a big plus for me. And what are the downsides so far? So it doesn't do, I think it has the potential to do this, but so far, at least in the way that they have described using joints and everything, it won't work for facial deformation, but I think it could be adapted. I mean, I might be wrong. It might be a more difficult problem. People might be more susceptible to errors in the facial deformation, but I think it's something that should be tried. Okay, so this is what I had to talk about this paper. I hope you enjoy this. I hope you can see that it's not really something that no one can implement. It's a really neat idea, but the implementation is not that hard. And I hope you can see that by using the examples I have made available in the site. Next week, I'm going to talk about this other paper called Mode Adaptive Neural Networks for Quadruped Motion Control. This was a big hit when the SIGGRAPH Tech Papers video came out, and this was also the most voted paper in our pool, so I think you're gonna like this a lot. If you have any suggestions on the format of these videos or the content, please share. I haven't finished the video for this one yet, so I'm really interested in knowing your opinion. And if you like what we're doing, please consider sharing our work on your social networks or to your colleagues. This is really the best way to support what we're doing here. Thank you very much. I'll see you in 2 weeks, and cheers!